Transistors Application AC Amplifiers, Eugene Melkoff College, William and Mary, Week 7. Advantages, summary of simple emitter follower. Advantage, input impedance increases, input impedance, input is beta resistor emitter. Power current gain, output depends on beta, simple. Summary of simple emitter follower. Advantages, increase impedance increases, impedance increase equals beta resistor emitter. Power current gain, output depends on beta, simple. Disadvantages, input signal must be positive. Even more, it should be above 0.6 volts, no voltage gain. Real life signal, and real life signals usually swing around zero. In real life signals, we need to do something with our simple emitter follower. Solution 1, push or pull follower. Solution 2, AC coupled bias amplifier. Alright, your negative, positive, negative emitter follower shows voltage, constant current, voltage input, voltage output going in your negative emitter going to the resistor, the base. Negative, positive emitter follower shows the lines, 0.6 volts, red and blue. Negative, positive emitter follower, positive, negative emitter follower, negative, positive emitter follower, positive, negative emitter follower, and then it shows your push-pull emitter. Basically, it has two voltage inputs, two bases. Your voltage is going around the emitter, and then so this is a push-pull emitter. Push-pull emitter wave sounds very closer together, and then it shows 0.6 volts. Push-pull emitter follower crossovers. Push-pull emitter improved. Push-pull emitter improved. Now it shows resistors in between and diodes and the voltage input. So that's pretty good. That's improved. Push-pull emitter follower improved. AC coupled emitter. AC coupler emitter follower. Design maximum output is voltage emitter equal to voltage constant current over 2. Disregarding voltage base emitter is 0.6 volts. Volts base equals voltage emitter equals voltage constant current over 2. Thus resistor 1 is equal to resistor 2. Quiescent current amperes emitter is equal to voltage emitter over resistor emitter. We want amperes resistor 1 plus resistor 2 greater than ampere base. Factor of 10 scale safe margin 1 ampere resistor 1 plus resistor 2 equals 10 amp base collector equals 10 amp emitter over beta. Thus resistor 1 equals resistor 2 equals resistor emitter beta over 10. From the AC point of view, the input of the RC high pass capacity is equal to capacitor 1. Resistor is equal to resistor 1 parallel, resistor 2 parallel, beta resistor emitter. Therefore, 3 frequencies of D and B is equal to 1 over 2.5 over times 1 over C1, R1, parallel, R2, beta resistor above all rules. R is congruent with R1 over 2, approximate R1 over 2. So we have a constant R1, R2, beta resistor 3 on the bottom. From the AC standpoint, input resistor, capacitor, high pass capacitor is equal to 1, capacitor 1, resistor is equal to resistor 1, resistor 2, the resistor 1 parallel, resistor 2 parallel, beta resistor emitter. Frequency of 3 decibels is equal to 1 over 2 pi times 1 over capacitor 1 times resistor 1 parallel to resistor 2 parallel to beta. Resistor emitter were above rules. Resistor is congruent with resistor 1 2. Output of RC is high. Capacitor is equal to capacitor 2. Resistor is equal to resistor load. Frequency of 3 decibels is equal to 1 over 2 pi times 1 over the capacitor 2. Resistor load. For unloaded filters, resistor load is greater than resistor emitter. Factor of 10 of safe margin of resistor load is equal to 10 times the resistor emitter. Common emitter amplifier. Ampere current is equal to ampere emitter equal to voltage in of 0.6 volts over resistor emitter. Voltage out is equal to voltage constant current minus resistor current. Resistor collector, ampere collector. Voltage output is equal to voltage constant current minus voltage collector times voltage input minus 0.6 volts over resistance emitter. Voltage output is equal to voltage constant current times plus 0.6 volts times resistor capacitance, resistor collector over resistor emitter minus voltage input over times resistor collector over resistor emitter. Gain is equal to negative resistor collector over resistor emitter. Attractive to put resistor emitter at 0. Transistor models fail. Transistor emitter resistance resistor emitter is equal to 25 millivolts over ampere collector. Gain or G is equal to negative resistor collector over resistor emitter. Your AC common emitter inverter amplifier. Design chosen gain is equal to resistor current collector over resistor minimum maximum output. Voltage current is equal to voltage collector is equal to constant current divided by 2 quiescent current. Ampere current ampere collector is equal to voltage constant current minus voltage collector over resistor collector equal to voltage constant current times 2 resistor current collector is equal to voltage constant current divided by 2 times amps collector. Resistor emitter is equal to resistor collector divided by gain. We want ampere to resistor 1 plus resistor 2 to be greater than the ampere at the base. Factor 10 scale safe margin. Voltage base is equal to voltage emitter at 0.6 volts. Resistor 2 is equal to divided by resistor 1 plus resistor 2 is equal to voltage base over voltage constant current. And that was the slides for transistor application AC amplifiers week 7. And now we'll move on to chapter 7, which is 6 pages. Alright, the transistor amplifier study for the last chapter. Some of the serious problems with the AC signal. The most serious shortcoming is the dead region in which small signal do not turn on the transistor. Some of the signal is smaller than 0.6 volts. If it is negative, the transistor does not conduct, the amplifier does not work. Design goal to for an AC amplifier. Before moving on to make a better AC amplifier, let's define some of the useful terms. We define the output range. The range of the possible output voltage refers to the maximum minimum output voltage as rail voltage, or an output swing is the difference between rail voltages. The input range of the range of input voltages produce output where there are not either rail voltages. Our goal is to design AC amplifier the input and output range with symmetrically around 0 to ensure that there is no dead region. To this, we need to make sure the transistor is conduction of all our input ranges. That he does the work. Why do it? By adding offset voltage and input to make sure that the voltage presented with the transistor base with no input signal. And this is the resting or quiescent voltage is well above ground. In label 6, the function generator provided with the offset in chapter, we will show how to design an amplifier provides its own efficient offset. Now, understanding capacitor pretty easier how to add and subtract an offset voltage signal, at least AC signals. Here we will design transistor circuit with a bias network. The bias network is simple. The voltage divider that is connected to the input, its job is to ensure output stays approximately half the supply voltage from small input signals. The output voltage can vary only over a wide range of positive and negative, which allow for the keeping of the transistor conducting. The trick to make this work is separate the quiescent voltage and current from input and output voltage. Due to this, blocking capacitors isolate the input and output. In connecting AC input capacitors, it will not pass a DC output offset voltage. but it does pass a fast AC signals. Similarly, output blocking capacitor will pass the first fast signal while keeping the quiescent resisting voltage from the amplifier of the distributing whatever comes next. This is shown schematically as the first figure next page. Some design basics. There are weeks going on redesigning emitter, follower, inverter, amplifier to use basic networks to help you with your design. You will make a step-by-step list for the design of each of the three basic transistor circuits. Here are a couple of initial decisions we will make. You will begin determining the quiescent of the DC no signal current through the collector of the UG of the quiescent current to the large any of the current you will use to drive the load. Quiescent current 1 milliampere is typical. We'll use that in our example design. We will use a signal plus 15 volt power supply to power the collector of the common collector voltage or VCC. For this bias network, you need careful loading of the different stages of the amplifier of the transistor base current load output bias voltage divider. The bias base will need stiff voltage divider low impedance on the rule of thumb. For designing voltage dividers, we have a factor of 10 differences in impedance for each stage. The emitter follower. Alright, the design steps of the emitter follower. Figure 7.1 produces for all of the maximum symmetric range of the output values, voltages. You would be on your quiescent base voltage would be half of the 15 volt supply voltage. So we use a 1-to-1 input voltage divider. This means that both biasing resistors will be the same. 2, when we choose an emitter resistor with a quiescent voltage emitter diode drop below the voltage middle of the bias network. If we have the 1-to-1 divider, thus roughly 7 plus volts in our case. To get our design quiescent current emitter resistor must be resistor emitter is equal to voltage emitter over the ampere emitter equals 7 volts over the 1 milliampere equals 7 kilo ohms. We use a standard 6.8 kilo ohms. It was close enough to the bias. To the bias, we want to stiff the voltage of the divider low impedance. Therefore, we want to use a resistor smaller than the base emitter ground impedance. By a factor of 10 or more. So, for example, we'll choose the 70 kilo ohm resistor for the divider. Remember the AC coupled to Viva, the capacitor input-output exact value of the particular important, though you should remember that you are making a bias high-pass RC filter. Values around 0.1 ufrads, typical as shown in what is frequency of 3 decibels, 20 hertz, but can use what you have long as not. But you can use what you have as long as it's not too small. With common emitter and amplifier in the circuit, we need to know the quiescent current with the design gain. Let's assume the gain of negative 5 amps of 1 milliampere. The quiescent current with example the circuit diagram is shown in figure 7.2. In this current, we want the quiescent output at the collector to be set roughly at halfway between the power supply and the ground. Maximum output voltage for 1 ampere collector equal to 1 milliampere. Resistor collector equal to voltage collector over amp collector equal to congruently 7 volts amps over the 1 milliamp or 7 ohms. We will use the standard resistor about the value of the resistor collector at 6.8 kilo ohms as we follow. The emitter resistor determined with the desired gain. Previously, we saw the gain of the resistor collector over the resistor emitter. In our case, we want to gain 5, so we choose resistor emitter of 1.35 kilo ohms, or approximately by the standard 1.5 kilo ohm resistor. Note that it will choose the emitter quiescent voltage will give the voltage dropping off the emitter of the ampere current ampere collector voltage emitter equaling to 1.5 volts. The tricky part of designing a bias network in the circuit, we know that the emitter voltage output of the bias network with the base voltage is just the diode drop higher with the emitter voltage. Therefore, base resistors must be given the base voltage base of the voltage base equal to voltage 2 equal to voltage emitter plus 0.6 and is 2.1 volts. The drop across the lower 2 bias resistors, others drop at the voltage 1 equal to voltage constant current minus voltage 2, giving us 12.9 volts. The bias network output impedance must be small enough to keep the bias even when loaded. We will select the bias resistor so that the current running through the bias network is about 10 times larger than the current that goes into the base of the base beta of 100, and then the base current is amp base is equal to amp current collector divided by beta equaling 10 micro amps. The bias is current. The amp bias is 10 times larger than large amp bias equal to 100 U amps. Total resistance of the bias network resistor 1 plus resistor 2. 150 kiloohms, we could determine the resistor 2 since the voltage divider formula, voltage base over the voltage constant current equals resistor 2 over resistor 1 plus 2, resulting in resistor 2 and 21 kiloohms. Therefore, resistor 1 is 150 kiloohms minus 21 kiloohms, 129 kiloohms. Remember the AC couples with the input-output capacitors. The values are not particularly important. Relevant the RC time constants that should be chosen as a guaranteed unimpeded passage of the AC signal to be amplified. And then it goes into some design exercises in the lab. And these were the notes from Chapter 7 of AC transistor amplifiers.